So this is a quick summary of section 7.1 to 7.5 inclusive for chapter 7 of the math textbook. So section 7.1 was about developing systems of linear equations. The focus was on understanding how we could read real-world scenarios and then create a system of linear equations. So the concept of 7.1 is that a system of linear equations consists of two or more linear equations with two unknown variables that need to be solved together. So in chapter 6 we just talked about linear equations, which is where we took a real world scenario and we created an equation that ultimately had one unknown variable. Examples would include you want to find out what the profit of a school dance is, and it costs so much per ticket at a school dance, plus there was a flat fee that the student council had to pay the DJ. So you'd create some sort of linear equation like profit equals, $5 per ticket, N, because we don't know how many tickets were sold, plus $300 for the DJ. So we were able to create a linear equation with just one unknown variable, the number of tickets sold. As soon as we figured out the number of tickets sold, we had our answer. That was an example of a linear equation, where you created an equation from a real world scenario that only had one unknown. And we were able to solve it by isolating for that variable and so forth, using all the techniques we learned. With a system of linear equations, we're going to read a real world scenario and we're going to model equations, but we're going to get two equations that each have two unknowns. They're in terms of two variables. And we can't solve an equation that has two unknowns with just one equation. But luckily, the scenarios will kind of have extra information that we're able to create two equations, each with two unknowns, but we're able to use that to solve. The general rule of thumb is that you need an equation per unknown. So if you have two unknowns, you need two equations. If you have three unknowns, well, you need three equations, and four unknowns, four equations, and so forth. But when you get dealing with that, you won't be doing linear equations solving. You'll typically be using something called matrices. But so that's what a system of linear equations is. It's really just two or more linear equations, each having two unknown variables, and they need to be solved together. So each unknown variable requires an equation, as I just said. Here's an example. A school has buses that carry 12 and 24 passengers, and there's a total capacity of 780. Out of this company's buses, they can have a total capacity on all their buses of 780. And there are 20 more small buses than large buses. So we're going to let the variables, we're going to let S be small buses and L be large buses. Those are the variables we choose. We could have just chose X and Y as normal, or we could choose anything. Variables are just, you can choose whatever you want. It's just representing an unknown value. So the equation that we can come up for the first part of the question, the sentence highlighted in red, is 12S plus 24L equals 780, meaning there's 12 people that can fit in a small bus plus 24 people that fit in a large bus, and the total capacity of all of the small buses and all the large buses equals 780. That equation alone wouldn't be enough for us to solve for the variables S and L, because we have two unknowns in one equation. Luckily, the statement has more to it. It says there's 20 more small buses and large buses. So we can create a second equation where we say S equals L plus 20, because we know there's 20 more small buses, so whatever L is, which is an unknown value to us, but it does represent a value, well, you add 20 to that, and that's going to be the number of small buses. So now between these two equations, we'll be able to solve for both variables. But in section 7.1, it wasn't about solving. It was about reading some situation, analyzing something, and creating a model for it, creating a system of linear equations, i.e. creating a couple of equations. So 7.1 was just about creating the equations from some real-world scenario. And then you were just given values for the variables already solved for you. So they were just told to you, like in one of the examples, Denise just tells you what the width and length of a parameter were of a stage, and you just had, or a flag rather, and you just had to plug it in and into your equation and verify that when you plugged in the values for S and L into your equation, that this ultimately equaled 780. And when you plugged in the value for S and L into this equation, that the left side equals the right side. So verifying an equation is just plugging in the values for the variables and verifying that the left side of the equation ultimately equals the right side of the equation. But 7.1 just dealt with creating the equation, the system of linear equations, from some real world scenario. In 7.2, we started talking about how to solve systems of linear equations. So we still had to create them from some real world scenario. We still had to get the linear equations in the first place, which are the two equations. But then we had to solve them by graphing. Now, a lot of times we actually didn't have to create the linear systems. For time, the math book just provided it to us. In the real world, we'd still have to create them. But because we were already tested on that in 7.1, they want to speed things up a little bit, so they just give us the equations and say solve them by graphing. So how do we do that? Well, we have to take each linear equation and we need to put it in slope-intercept form. And that was discussed a lot in chapter 6, where there was a lot of different forms that we could put a line in. There was slope-intercept form, there was point-slope form, there was kind of the form slope equals slope, which was y minus y1 over x minus x1 equals y2 minus y1 over x2 minus x1, that sort of thing, which essentially was a slope equals slope. And then there was the general form. But the slope-intercept form is kind of the most intuitive, I would say. So you're going to take your linear equations that you were either given or that you have to find for yourself, and when you put them in slope-intercept form, you're very quickly going to be able to see the slope, whatever the coefficient of the x variable is, or your independent variable, and then the constant is going to represent your y-intercept. So put each variable in slope-intercept form, and then you're going to plot them on the same coordinate plane, the same graph, and then the intersection point where those two lines intersect after you graph them, that represents your solution to this linear equation. And the good thing about graphing is that it provides a visualization of what's happening. You're not just doing math, you're not just plugging and chugging numbers. It actually is showing you, oh, this is what it means by a solution, where I find, a set of values for the variables, like an x value and a y value, that solve both equations simultaneously. That's kind of abstract when you think about it with just the math algebraically, but when you actually plot both lines on a graph, you can see what that means. Oh, the x and y value have to satisfy both equations. Oh, it's the intersection points where this line has that same point and this line has that same point at their intersection point. So it's a little easier to visualize with graphing. That's the good part about graphing. It's intuitive. The bad part is it's very time consuming to graph, and it doesn't yield a precise answer, at least not most of the time. It's going to give you an approximate answer, which is not always what we want. But the idea is that you're going to solve the system, in this case x plus y equals 7 and 2x minus y equals 1, by graphing. And that yields an intersection with a coordinate point of 3, 4. So an x value of 3 and a y value of 4. That point is at the intersection where both lines cross. So I've shown how to do it here. So if you take the first equation of the linear system, and remember there's always going to be two equations, this would be the second equation. We take the first equation and we're going to put it in slope-intercept form. So I want to leave the y on the left side, but I want to move the x on this side. And whenever you take a variable and switch it to the other side of the equal sign, so if I take this x and put it on this side, I'm going to have to flip the sign. So it's positive over here, so it's going to become negative over here. I've done it the long way and show that really what you're doing is subtracting x from both sides, because you want to get rid of it on this side and put it over here. So if you subtract it from both sides, x minus x, well, they'll cancel out, and you'll be left with a negative x on there. However you want to think about it, whether you just move it like how I normally think of it or do this long way, it's up to you. Ultimately, you're going to end up with y equals 7 minus x. But we want to make it, even though that's accurate, that's technically correct, we want to put it in slope-intercept form, so we want to move the x as the first thing. So negative x plus 7, because this is now more intuitive for us to see, okay, the slope is negative 1, because when there's no coefficient in front of a variable, it's assumed to be 1, so it's just implicitly 1. So we have negative 1 for a slope, meaning it's going to go vertically down for every 1 it moves over, down. And 7 is our y-intercept, so this line is going to cross the y-axis at positive 7. So now we have that equation in slope-intercept form. Let's put the other one in slope-intercept form. So the other equation is this, 2x minus y equals 1. So in slope-intercept form, we are going to, again, we want the y on this side. So we're going to move the negative 2x here. Now, you could have obviously done this easier by moving this negative y over here, and it became positive, and moving the 1 over here to become negative. That's how I would actually do it, but I did it this way just to make it a little more clear what's happening. But really, you could have just moved this y over here, became positive, and it would have been y, and then move this 1 over here. It would have been y equals 2x minus 1, which is ultimately what it is down here. But this is the long way to do it. Negative y, because I'm moving the 2x over here. So it becomes 1 minus 2x. Then because it's negative y, and we don't want to solve for negative y, the slope-intercept form is not negative y equals mx plus b, it's y, positive y. So we got to times both sides by negative 1 to get rid of the negative here, because again, timesing a negative by a negative is a positive. So we'll be left with y here, and we got to distribute this negative 1 across both terms. Again, make sure you distribute it. So it's negative 1 times 1, which is negative 1, and negative 1 times negative 2, which is positive 2x. And again, I get it in this form originally, which is correct, but again, I want to move the x variable and its coefficient here so that I can see that the slope is 2 and the intercept is negative 1. So this just kind of shows what I did. Again, step number 1, put each linear equation in slope-intercept form, y equals mx plus b. And then, whatever you do to one side of an equation, you have to do to the other side. You must balance the equation. So when I subtract x from here, so I could get rid of this x over here, I had to subtract x from this side. When I wanted to get a positive y, I had to times negative y by negative 1 to get a positive y. I had to times the whole other side by negative 1. So you must balance your equation. And then finally, once you're in slope-intercept form, the coefficient in front of the independent variable, i.e. in front of the x variable in this case, so 2 in this case and just negative 1 here, that's the slope. And the constant, which is in pink here, is the y-intercept. And the y-intercept is, again, the point of your line that, it's the y-coordinate of the point on the line that crosses the y-axis. So that's what section 7.2 was about. It was about solving linear equations, or systems of linear equations via graphing. It's intuitive, it's easy to visualize the solution because it's the intersection of the graph, but it's time consuming and it doesn't yield accurate, precise results most of the time. It gives you an approximation. So section 7.3 is really just an extension of 7.2 in the sense it uses graphing in order to solve the equation, but you don't have to do the work. So it helps free up a little of that time factor. Basically, it utilizes technology, calculators, graphing software, whatever. And you're just going to input the equations. So you're going to take the equations. You still need to put them it's in the calculator. You just need to type them in the calculator in slope-intercept form. So you still have to take the equations, put them in slope-intercept form the same way you did in the graphing section. But this time, once you have them in slope-intercept form, you don't have to do the graphing. You just type them into your calculator, and that's going to be very calculator dependent how that's done. But you type them into your calculator, and you press a couple buttons, and it magically will graph it for you. And a good graphing calculator will actually show you the graph and the intersection point. So it makes it a little quicker, so it takes away that time factor that's a negative of the graphing method, but you still get non-precise answers, so you still don't get like accurate answers. And it's still, I would still argue, it is still time-consuming typing it in the graphing calculator, which is why I prefer the substitution method. So section 7.4 utilized the substitution method, and that's how they solve linear equations. So instead of graphing, which again is time-consuming, very cumbersome, and yields approximate results, we're going to use an algebraic method, so just using math to solve systems. And the way this works is we solve one equation for a variable. Doesn't matter which variable, pick one. There's going to be things I talk about why you might pick one over another one because it's easier, but at the end of the day, it doesn't matter. Whatever variable you choose, if you solve for it, you'll ultimately still get the right answer in the end. It just might be harder for you to get there. But you're going to solve one equation for a variable and substitute it into the other equation to find the other variables. So the importance here is that substitution simplifies the solving process compared to graphing or anything. So as I said, typically one equation will be easier to solve for the variable in terms of the other variable. So if there's an equation with a variable that has a coefficient of 1, meaning you won't see a 1 written, it's just implicitly there'll be a 1, meaning if you have a variable that's just x or just y, meaning it has a coefficient of 1, that's the one you want to solve for because it's already very simple. So here's an example. For this system of linear equation, which has 2x plus 3y equals 12, and the second equation is x minus y equals 2, we're going to first solve this equation for x. And do you see why I would choose this one over this one? This one is complicated. Both the variables have coefficients other than 1. The x has a 2 coefficient, the y has a 3. So even if I move everything, let's say if I solve for x and I move the 3y on this side, I'm still going to have to get rid of this 2. So I'm still going to have to divide both sides by 2, which is going to result in fractions and just things that aren't as easy to deal with. Will we still get the same answer then? Absolutely. But it is more cumbersome, and it's just more math. And, as much as we all love math, we don't want to do more of it than we need to. So whereas x minus y equals 2, in this case, both variables have a 1 coefficient. So solving for either one of them would be easy. But why would we choose the x over the y? Well, because the x has a 1. There's nothing there, so it's an implicit that it's a 1, a positive 1. The y has a 1, but it's a negative 1. So because it's a negative 1, we can solve for y, and it'll be pretty easy, but then at the end we're still going to have to times both sides of the equation by negative 1 to get rid of that y, just like we had to do up here. We had a negative y, so we had to times this side by negative 1 in order to get rid of the negative, and whatever we do to one side of an equation, we have to do to the other because we must balance our equations. So in this case, this was the clear one to do. But don't worry, you don't get caught up too much in the fact of, oh, did I choose the right one? It doesn't matter. We're just saying if there's an easier option that sticks out to you, solve that one, and it'll just be easier for you. But if you choose, there's no wrong one to choose. It'll ultimately work out to the same answer. That's the beauty of math. So I've done the solving down here. Basically, I've got the two equations. The first equation is here, and I've labeled it equation 1. The second equation is here, which is labeled equation 2. And I'm going to choose the second equation as the easier one. Again, because it's got this 1 coefficient, just a positive 1. So I'm going to solve the easier equation for one variable in terms of the other variable. So what does that mean in terms of the other variable? It means solve x by moving the other variable on the other side, and now x equals 2 plus y. You need y to solve x. It's basically saying in terms of the other variable, it means that you're not just getting a number. It's not like x is 7, which we're used to. That's what we like. No, it's going to be x equals something plus a variable. Or it could just be that variable for that matter. So again, we chose to solve for x in terms of y. And now the reason it's called the substitution method is because now we go back to the first equation, the one that we didn't rearrange and solve for a variable. We go back to the first equation, and everywhere we see an x, we're going to substitute in the value for x. So in this case, 2 plus y. So 2x plus 3y equals 12. Now it's 2 instead of x. I'm going to substitute in the value that I got for x, which is 2 plus y. And I'm going to substitute that in here. And I'm going to solve as normal, so I'm going to distribute my 2 across the parenthesis. So 2 times 2 is 4. 2 times positive y is 2y. And now I'm going to group like terms. So you can see I have a positive 2y. I have a positive 2y and a positive 3y. Well, that groups together to be positive 5y. And then I'm just going to do the regular thing. I now want to solve for y, because now the whole point of substituting is now I've got an equation in terms of just one variable. See, even when I distribute out here, I'm just going to be in terms of y, just one variable, and that's easy. We've been solving equations with one variable forever. We know how to do that. We just need to isolate the variable we're solving for by moving everything we can to one side opposite of the variable, and then if we're left with any coefficients on the variable, we just get rid of them by dividing or whatever. So we do that. We get down to this point, and we're like, I need to solve for y, so I'm going to take this 4 and move it over here. So it becomes negative 4, subtracted from both sides. And now we're left with 5y equals 8. Well, I need to get rid of this 5, so I'm going to divide both sides by 5. And y equals 8/5. So now you'll know I have a value for x, but it's in terms of y. But I have an actual value for y now, a number. So now I can take that actual number that I got, the actual value for y that I solved, and I can plug that into either of the other equations. It doesn't matter which one. Again, I always go with the easier one. And when I do that, I'll actually figure out what x and y is. So I didn't show that here because it shows up here. But basically, if I was to put 8/5, so 8 over 5 in here, it'd be x minus 8 over 5 equals 2. I would take that negative 8 over 5, put it on this side, and be 2 plus 8 over 5. I'd have to find a common denominator, so 2 plus 8 over 5. Well, 5 is the denominator here, and 2 can be thought of being a fraction 2 over 1. So I'll times this whole fraction by 5 so that I have a common denominator of 5, and 2 times 5 is 10. 10 plus 8 is 18. 18 divided by 5, that would be x. Again, I didn't, ultimately what you're gonna get for an answer is y equals 2, because I'm not sure if I did the math there correctly. Y equals 2 and x equals 4. I didn't show that part, but once you have solved for one variable and you actually have a value, not in terms of something, but just a value, just substitute it into either of the other equations, and then you'll be able to solve for the other variable, x. Like I'll actually be able to solve it and get a number, and then I'll have both values, like y equals 2 and x equals 4. So again, this is just reiterating what I said. You're going to substitute the value you obtained for one of the variables, i.e. the x variable in this case, into the other equation to get an equation now with only one variable. So again, when I have the equation here, it's only in terms of one variable, just in terms of y. We're used to solving that. We've already been solving equations with one variable forever. So this makes it easy for us to solve. Finally, in section 7.5, we're introducing another mathematical way to solve a system of linear equations. So again, graphical was how we solved it in section 7.2. It's intuitive, you get to see the solution, the intersection of the lines, but it's time consuming and it's not precise. Graphing technology takes away some of the time consuming, makes it a little quicker because you just have to plug the, you just have to put the equations in y equals mx plus b form, into slope-intercept form, and plug them into your calculator, and the calculator does the work. But you still, it might be a little quicker, but you still don't have a precise answer. You still have an approximation. Doing it the substitution method, you're doing it algebraically, it's usually a little quicker actually to do the math, and you have an exact answer. Well, elimination is just another method that's using math, not graphing, but it's not using substitution. It's the elimination method to solve linear equations is where you need to adjust the equations either by multiplying or adding, or you could by dividing or subtracting as well. It's kind of it's implied here, but adjust equations to eliminate one variable, and then you'll be able to solve for the other variable easily. Same in substitution, same as within substitution. Once we eliminated one variable, i.e. solving for x in terms of y, and we plugged in x here in terms of y, well, once we have an equation with just one variable, we're easily able to solve it. So that's what we're going to do here. We're going to eliminate one of the variables, and then we'll just have equations with one variable in them, and we'll solve them. So again, elimination can be effective when the equations are structured for easy cancellation of variables. So it's going to maybe take a little bit to get used to find out which equations lend themselves better to solve by substitution or by elimination. But the general rule of thumb is if you're looking at a system, like this system here, this is one equation, and this is the second equation. If you see something where the coefficients on either of the variables are the same, or they're different only by their sign, like this is a positive 2 and this is a negative 2, that equation, that system of linear equations lends itself very well to elimination. Because if they're the same in this sense, but they have opposite signs, you can add the equations together, which is what I've done here. I just don't have the add sign, actually, I just realized. But you can add the equations together, and adding a positive 2y plus adding a negative 2y, they'll cancel out. And we'll eliminate our y variable altogether. Therefore, now we only have two equations in terms of x, which is amazing. If they were the exact same value, meaning they both had the same sign in front of them as well, not just the number, then we could just subtract the equations from each other. And positive 2y minus positive 2y is the same thing as positive 2y minus 2y, and they still cancel out. So either way, whether you're adding equations together or subtracting, depends on the sign, but you just add or subtract or multiply or divide, whatever you need to do in order to cancel and eliminate a whole term, one of the variables. So again, I've showed here, this is one equation, this is second equation. I've lined them up. Make sure you line them up like x variables to get in line with the y variables together in line with the constants. And I don't have a plus sign here, but there should be a plus here and a line indicating them adding these two. But 3x plus 4x equals 7x. 2y minus 2y, so positive 2y minus 2y, well, that they cancel out. And it's 0, so I haven't included them here. And 12 plus 2 equals 14. And then you just have now a linear equation with one variable, which you can easily solve. Divide both sides by 7. Now you have x equals 14 over 2, which simplifies to x equals 2. And now, once you have a value for one of the variables, x equals 2 in this case, you just plug that value into either of the other original equations in for x, and you can solve that equation now for the other variable. And once you have the other variable, now you have your solution. X equals 2 and y equals 3. This is the solution for both equations. So I've shown here, I've substituted x equals 2 into this equation, 4x. I don't know why I chose that, I just did. Again, it's arbitrary, I could have chose either one. In this case, there was really no easier one, so I just chose the second one. 4x minus 2y equals 2. Well, that's 4 times 2, because x is 2, remember? That ultimately allows me to figure out that y equals 3. So what did this summary cover? This summary covers the essential teachings of each section along with corresponding examples to solidify the understanding of linear equations and their solving techniques. So that's the aim of this. We've went through this all, Emma, in this chapter. Again, we've been through section 7.1, which again was just, the idea was just to make a connection. We were just trying to look at some real world scenario, whatever it was, the buses, the capacity of buses, or the parameter of the flag, if you remember all this stuff. And we just had to create a system of linear equations, two equations that were related, but each equation had two unknown variables. We just had to create them, and ultimately then we verified that we were correct by someone gave us the answer. We were given the variables at the end. That's all 7.1 was doing for us. We were just creating the system of linear equations, the two equations, from some real world example. In section 7.2, again, we were now graphing this system of linear equations. We were graphing each equation after putting them in slope-intercept form, and then the intersection point of the graph, that represented the solution. Then section 7.3, we were still graphing, we just weren't doing all the work. We were getting a system of linear equations, which are two equations, and we were putting them in slope-intercept form. But then instead of us doing the work, we were plugging them into the calculator, and it was giving us the answer. And then in section 7.4, that's where we started to actually do more of the math. We took the system of linear equations that either we figured out through some real-world scenario or that we were given, and what we did is then we solved for one of the variables in terms of the other and substituted that value into the original equation, and we were actually able to solve for the x and y, or the two variables. And then finally in 7.5, we use the elimination strategy where we line things up. So we lined up a couple things together. In this case, these both have a positive, the y variables both have positive 1 as their coefficient, so positive y and positive y. So when we subtract those from each other, we ultimately get rid of the y. One big thing to remember when you're subtracting using the subtraction method, that subtraction sign needs to be distributed throughout everything in parentheses. So the negative has to go on the x, it has to go on the y, and it has to go on the negative 4, thus making the negative 4 a positive 4. That's something that sometimes might cause you to lose marks if you forget to do it, which is why they have this little yellow sort of note here. Why did we put brackets around equation 2 when we subtracted it? It's so that we know to distribute this negative sign across. Anyway, that's kind of the summary. I'll just read this further too. This is just kind of a little more, but if you're done listening, which at this point you might be because it's already been 27 minutes, feel free to end it. I'll just read this really quick. The text focuses on systems of linear equations, outlining their definition, various methods to solve them, and practical applications, particularly in the context of real-world scenarios like modeling reactions of polar bears and calculating capacities or cost. That's when we took the real-world scenarios, like we needed to figure out the parameter of a flag, or the dimension of a piece of plywood, or the profits got from returning a certain amount of bottles and cans based on the deposits that we would get back, the refunds rather. So that's what that is. Systems of linear equations is we're taking real world scenarios and creating these equations. So a system of linear equations consists of two or more linear equations involving the same set of variables. And two or more, but for high school I think it's just two. So a system of linear equations is two equations. And the solution to such a system is a set of values for the variables that satisfies all the equations simultaneously. So that's important. When we come up with a solution, like we find out the x and y variable, or the dependent and independent variables, the two unknowns, those two unknowns satisfy both equations. They will solve both the two equations because the equations are related. So the text highlights such systems can have one solution, infinitely many solutions, or no solutions at all. So that's important. Systems of linear equations can't have three solutions. That's not a thing. They don't have 4 or 5 solutions. They have one unique solution, which is what all of our examples so far have taught us. But presumably going further in section 7.6 and 7.7 and so forth, which we haven't got to, then we'll start talking about when you can have no solution or infinitely many solutions. But that's it. It's either one solution, no solution, or infinitely many. You can't have 7 solutions. Finally, we started discussing various strategies for solving these systems of linear equations, including graphical methods and algebraic methods. Algebraic methods being substitution method and elimination. In graphing methods, each equation is plotted on the same coordinate plane, and the intersection point of those lines represents the solution. However, this method can be cumbersome and may yield approximate rather than exact values. Hence, algebraic methods are preferred, in my opinion. But again, the graphical method, the big problem is that they're time-consuming, cumbersome, like just difficult, and they're only approximate values. But again, the answer is when you plot both lines on the same coordinate plane, so you do have to put the equations in slope-intercept form, y equals mx plus b, and if you plot them both on the same coordinate plane, the intersection point is the solution. But because it's cumbersome and they're approximate values, and we want exact values in math, we're going to use the algebraic methods a lot, which are substitution, and elimination. And so things like substitution, they are emphasized for their precision. They give you an exact answer. So in substitution, we take one equation and we manipulate it to express that one variable in terms of the other. So we can express x in terms of y or y in terms of x. It doesn't matter. I mean, typically you're going to choose the easier one, but you're expressing one variable in terms of other. You're solving one variable. You're solving for x in terms of y. So, and then it allows you to substitute the value you got for one of those variables. So let's say the value you got for x. It allows you to substitute that into the second equation that is two unknowns, x and y. Well, you substitute the value of x in for x. And because we know the value of x is in terms of y, now we have a single equation that is only in terms of one variable, like let's say y. And we've already been solving equations in terms of one variable forever, so that's amazing. We can solve that easily. This textbook also showed us how to form linear systems using the real-life examples. Again, demonstrating, determining the number of buses of different capacities required to meet certain needs, where, the small buses had a capacity of 12, the large buses had a capacity of 24, and the total capacity is 780, and we know that there was 20 more large buses or 20 more small buses than large buses. That example is a real-world scenario that we were able to model into linear equations. So that's what their purpose is, like, modeling financial scenarios like the investment rates of one of the examples. It emphasizes the importance of correctly identifying variables and creating equations based on the relationships expressed in the word problems. Moreover, so I'm just skipping that because that's just a specific example. Moreover, the possibility of creating equivalent systems is discussed. These systems yield the same solutions even if the original equations are manipulated, e.g. multiplied or divided by a non-zero number. This concept reinforces the understanding of how linear systems can be written in various forms while maintaining their fundamental properties. This is a very mathematical answer. So that whole thing, moreover, the possibility of creating equivalent systems just means that's a very complicated, convoluted way, and mathese, of saying if you do something to one side of an equation, you have to do it to the other side of the equation. We've talked about this a lot. You have to balance your equations. If I multiply one side of an equation by 5 in order to get rid of, the coefficient on some variable, I have to multiply the other side of the equation by 5. If I divide one side by something in order to, satisfy what I'm trying to do, I have to divide the other side of the equation by the same thing. If I add 5 to one side, I have to subtract 5. Whatever you do to one side of the equation, you have to do to the other side in order to keep the equation balanced. If you do that, you won't affect the equation. And that's what this mathese up here says in white. And this property is important because it's what's utilized for solving systems of linear equations using elimination, especially when there isn't immediately any similar coefficient of like variables to cancel out, and we have to find the lowest common multiple to eliminate a variable. So that's where I said with elimination, where we looked for variables that had the same coefficient. The signs could be different, but we wanted the same coefficient. If the sign was different, it just depended whether we added the equations together, subtracted them. But if we didn't have any variables that had the same coefficient, meaning both 1s or both 7s or something, but we had all different coefficients, then we would have to multiply either one of the equations or both of the equations by some factor in order to create a lowest common multiple, in order to create a couple variables that had the same coefficient. It's the same idea when we need to add fractions. We have to have a common denominator to add fractions. You can't add a half and 1/3. you have to get, multiply them so that you get 1/6, or that you have both denominators have a 6 in them. It's the same idea here. And the whole point of me saying if you do something in one side of the equation, you have to do it together, you need to balance the equations. Well, that means that we're able to multiply an equation by a factor, a scalar, like we're able to scale an equation by a certain amount, multiply everything in the equation by, let's say, 5, and the other equation by, let's say, 3, or if you need to multiply both equations, and you're not going to affect the overall equation. That's all that says. I know that's really confusing, but that's what the elimination process is based off of. Ultimately, you just want to be able to get rid of one of the variables, because remember, we have a system where we have two unknowns in each equation. That's really difficult for us to solve. By using the two equations and eliminating, arranging them in a way that we can add or subtract them or multiply them or whatever, and get rid of one of the variables, let's say x, well, now we've just got two equations in terms of one variable. We've been solving that forever. So that's one of the options. Again, we also talked about graphing technology, which was great for allowing us to visualize the equations and actually see the math, right? Using graphing calculators. But the problem was the answers were approximations, so they weren't accurate. And so what are some applications of linear systems? It extends beyond academic exercise, beyond the classroom. It's showing their relevance in fields such as economics, engineering, and environmental science. I mean, everywhere. Like math, as abstract as it seems sometimes, is used in the real world for things. Like optimization of cardboard boxes so that, a company uses the minimal amount of cardboard to get the maximum volume out of a box. Like things like that. Math is used in real world situations. Linear systems are used to model, analyze, and solve real-world problems that involve two or more variables that change linearly. And by change linearly, they would be graphed and make a line on like a quadratic equation or something that makes a weird loop sort of thing, like a U. So the focus on practical examples was such as attendance in events or demographic studies, enhances the relevance of linear systems in everyday decision making. So that's why there's so many practical examples in the textbook, just because they want you to realize that you're not just doing math for math's sake. You're doing it to be able to better understand the world and model the world mathematically so that we can solve problems. In summary, the chapter 7, section 7.1 to 7.5, hopefully this serves as a guide so that you'll be able to listen to it when I'm not available and learn from it. Because even though you're doing your test tomorrow for 7.1 to 7.5, again, math is cumulative. It just keeps building up on top of each other. So we had to learn, how to add and subtract, multiply and divide, and then we had to learn what variables were, and now we had to learn what linear equations was. That was all chapter 6, solving linear equations in terms of one unknown variable. Before we learned how to solve equations with two unknown variables, systems of linear equations. We had to learn linear equations, before learning how to solve systems of linear equations. So, keep this as a guide, and hopefully this gives you some information. But as always, if you need help, just come see me.